Welcome to the Deep Dive. Today, we're diving into something huge. Almost literally. Could we ever really travel between galaxies?
It's a great question.
I think about Andromeda, our closest galactic neighbor. It's, what, 2.5 million light years away?
Yeah, a staggering distance. Really puts things in perspective.
It makes any idea of just, hopping over there seem, well, impossible with current tech. Like, within a human lifetime. Forget it.
Absolutely. It's enough to make you think maybe exploring other galaxies is just science fiction forever.
Exactly. It can feel pretty discouraging, that scale. But what if there was a kind of cosmic shortcut? A loophole?
Like a way around the long way.
Precisely. And that's where this idea of wormholes pops up. You probably remember them from the movie Interstellar.
Oh yeah, the thing near Saturn that used to jump galaxies.
Right. Made millions of light years seem like nothing. And while that was, a movie,
The core idea isn't pure fantasy. It actually has roots in real theoretical physics, which is pretty wild.
yeah, it really is. So that's our deep dive today. What are wormholes? How might they work? What does the science actually say?
And to really get into it, we have to start with the big guy himself, Albert Einstein.
His theory of relativity, right, specifically general relativity.
Exactly, general relativity. He first presented it publicly back in November 1915. It's our foundational theory for gravity, for space-time itself.
And it's all wrapped up in these famous, or maybe infamous, equations.
The Einstein field equations, yeah. They look incredibly daunting on paper.
I've heard that, like 10 nonlinear partial differential equations, which apparently can be written as one tensor equation, but still.
Intense. Very intense, but the core idea conceptually isn't that complicated.
Okay, break it down for us then. What are they telling us?
Essentially, they describe how matter and energy tell space-time how to curve, and in turn, how that curved space-time tells matter and energy how to move.
Like the classic analogy, the bowling ball on a trampoline.
That's the one. The trampoline is space-time. The bowling ball is a massive object like a star or planet. It creates a dip, a curve.
And that curve is what we feel is gravity.
Exactly. More mass, bigger curve, stronger gravity. The equations quantify that relationship precisely.
So it dictates the shape of space-time itself.
It does. Now, what's really interesting is that Einstein himself, brilliant as he was, only found an approximate solution to his own equations for a very specific case.
Really? Not an exact one?
Nope. The first person to find an exact solution was Carl Schwarzschild, just a year later in 1916.
Schwarzschild, right. Know that name.
His solution described the space-time around a single perfect sphere of mass, not rotating, and it was huge.
Why was it so important?
Because it gave us the first mathematical description of, well, what happens when gravity gets really extreme. It predicted a point of infinite density, a singularity.
Ah, the heart of a black hole.
Precisely. His solution laid the theoretical groundwork for black holes, regions where space-time is so warped that nothing, not even light, can get out.
Amazing that theory predicted them so long before we, actually saw one.
Over a century. That first image in 2019 was a massive confirmation. But here's the twist.
Okay.
Those same Einstein field equations, they don't just have the black hole solution, they also have another theoretical solution.
Which is, don't tell me.
The wormhole. Or, more technically, the Einstein-Rosen bridge.
Wow.
Yeah.
Okay, so the same fundamental physics allows for black holes and these potential tunnels. How does that work?
Think of it like, well, a simple math equation, like x squared equals 4. It has two solutions, right? Plus 2 and minus 2.
Right.
Einstein's equations are vastly more complex, but they can also yield different possibilities. One is the black hole. Another, developed by Einstein and Nathan Rosen in 1935, describes this bridge-like structure.
An Einstein-Rosen bridge, a scientific term for a wormhole. Okay, so how do we visualize this? A bridge through space-time.
Let's use that paper analogy again. Imagine a flat 2D sheet of paper. 2 points, A and B, far apart.
Okay.
The shortest path is a straight line on the paper. But what if you fold the paper?
Ah, you bring A and B much closer together in the third dimension.
Exactly. You create a shortcut through the third dimension, not along the flat surface.
So the wormhole is like that fold, but for our 3D space, using a fourth dimension.
That's the idea. It's a theoretical tunnel connecting two distant points in our 3D universe by taking a shortcut through a higher, unseen dimension.
You also mentioned a map analogy, Delhi to New York.
Right. On a flat map, the straight line looks shortest, maybe cutting across Africa, but the actual shortest flight path goes way up north, near the pole.
Because the Earth is curved, a sphere. So the straight line on the flat map isn't the true shortest path in 3D.
Precisely. The wormhole proposes a similar thing by passing the vast 3D distance by taking a geometrically shorter route, possibly through this fourth dimension.
Makes sense. And the name wormhole, that came later.
Much later, yeah. 1957, physicist John Wheeler coined it. He used the analogy of a worm eating through an apple.
Instead of crawling all the way around the surface.
It just burrows straight through, a shortcut through the apple's fabric. Wheeler applied that image to the Einstein-Rosen bridge, burrowing through the fabric of space-time.
So the common picture, the two connecting two funnel shapes, that's just a visualization.
It's a helpful 2D representation of a complex 4D idea, yes. A real one might look more like a sphere, perhaps. But the crucial thing...
Still theoretical.
Still theoretical. Derived from the math, but never observed.
And if they do exist, there's this wild implication about time travel.
Theoretically, yes. If you could traverse a wormhole connecting two distant points faster than light could travel the normal way between them?
You could end up arriving before you left, in a sense.
Potentially. If the ends of the wormhole are moving relative to each other or in different gravitational fields, time could pass differently at each end. It opens up all sorts of paradoxes. Very theoretical, mind you.
Feels like we just stepped into a sci-fi movie again. Okay, let's pull back. What are the big problems, the challenges? First off, how does one even form?
That's a massive question. You'd need incredible gravity, like unimaginable forces to warp space-time that much to create an opening.
So, back to black holes. Einstein and Rosen thought they might be involved.
It seemed logical. Black holes are the kings of warping space-time. Maybe they could be one end of the tunnel.
But wait, if one end is a black hole, isn't that a one-way trip? You go in, you don't come out.
Exactly the problem. For it to be a useful shortcut, you need an entrance and an exit. If the other end is just another black hole's entrance, you're trapped.
So we need an opposite, something that lets things out.
Which leads us to another theoretical solution from Einstein's equations, the white hole.
White holes. Okay, the name suggests the opposite of a black hole.
Pretty much. Think of them as time-reverse black holes. A black hole's event horizon is the point of no return, nothing gets out.
Right.
A white hole's theoretical event horizon would be a boundary of no admission, nothing from the outside could get in. Things could only come out.
Like a cosmic fountain instead of a drain.
That's a good way to put it. The term white hole was first used, I think, by Igor Novikov in 1964.
Okay, so stuff comes out, nothing goes in. But how would they form? We kind of know how black holes form, collapsing stars and all that.
And that's a huge mystery for white holes. We don't have a known natural process that would create one. It's purely a mathematical possibility allowed by the equations.
Any speculation? Any wild ideas?
Well, one very grand idea is that maybe the Big Bang itself was effectively a kind of giant white hole, the ultimate eruption that created everything.
Whoa. The entire universe emerging from a white hole. That's big picture thinking.
Definitely. Another idea connects them back to black holes via Stephen Hawking's work.
Hawking radiation. Black hole evaporation.
Exactly. Hawking theorized black holes aren't truly permanent. They slowly evaporate over vast timescales. But there's a principle in quantum physics, the no-hiding theorem, basically saying information can't be truly destroyed.
So if a black hole evaporates, where does all the stuff that fell in go?
And one speculative answer is maybe it emerges scrambled from a white hole, which could be like the end stage of a black hole.
A cosmic recycling program.
Sort of, but again, highly speculative. We haven't seen black holes evaporate yet.
Seems like there are big hurdles for white holes too then. Any fundamental problems with the idea?
A major one is the second law of thermodynamics. Entropy disorder generally always increases in a closed system. Black holes are great at increasing entropy.
They scramble things up.
Right. A white hole, seemingly doing the opposite, spitting out organized matter and energy, looks like it might violate that fundamental law, like unscrambling an egg spontaneously. Physics tends not to like that.
So thermodynamics pushes back against the idea.
It presents a significant challenge. Still, there was that one weird observation in 2006.
Oh yeah, what happened?
The Swiss satellite saw a really bright gamma ray burst, GRB 060614, but unusually there was no supernova explosion associated with it, which is how we think these bursts usually happen alongside black hole formation.
So a bright flash, seemingly from nowhere.
Pretty much. And that led a few scientists to tentatively suggest, maybe, just maybe, it was a white hole briefly flaring up.
Wow. A potential glimpse, but still very uncertain.
Extremely uncertain, needs way more evidence. So Like black holes were for a long time, white holes are still firmly in the theoretical possibility camp.
Okay, so even if wormholes and white holes are mathematically possible, could we actually use them? Could a person or a ship survive going through one?
That's where most scientists get really skeptical. Even if they exist, they're predicted to be incredibly unstable, possibly collapsing instantly, and filled with exotic matter or lethal radiation. Traversability is a whole other massive hurdle.
Right. Doesn't sound very inviting.
Yeah.
But you mentioned something about magnetic wormholes
Where?
in a lab. That sounds different.
It is quite different, yeah. This was back in 2015. It wasn't about gravity or space-time. It was about magnetic fields.
Okay.
Scientists use special materials, metamaterials, to essentially channel a magnetic field. They created a situation where the field from one point seemed to tunnel invisibly and emerge at another point.
So like connecting a magnet's north pole to its south pole through an invisible path, skipping the space in between.
Exactly. They used yttrium barium copper oxide, a superconductor, cooled way down with liquid nitrogen. The magnetic field went in one end, vanished from the space around it, and popped out the other end.
So it mimicked the geometry of a wormhole, but for magnetism, not space.
Precisely. It showed you can create these tunnel-like field configurations, a very cool proof of principle, even if it's not getting us to Andromeda.
Still fascinating, though. And it reminds us that even if wormholes aren't the answer for FTL travel,
FTL being faster than light.
right, even if wormholes don't pan out, there are other ideas out there, aren't there? Still theoretical, but different approaches.
Absolutely. Like the Alcubierre drive.
Ah, yes, the warp drive concept.
Proposed by Miguel Alcubierre in '94. Also, interestingly, a solution derived from Einstein's field equations.
It all comes back to Einstein.
Pretty much. The idea there is you don't travel through space faster than light. You kind of scrunch up space-time in front of your ship and expand it behind you,
Creating a warp bubble that moves space itself around the ship.
theoretically allowing the bubble and the ship inside to travel faster than light relative to the outside space without the ship locally breaking the light speed limit. Again, huge energy requirements, exotic matter, highly theoretical.
It really is mind-bending stuff.
Yeah.
So wrapping this up, the universe is vast, travel seems impossible.
But the very laws that describe that vastness, Einstein's relativity, also contain these little hints, these mathematical possibilities, wormholes, white holes, maybe even warp drives.
All theoretical for now, definitely pushing the boundaries.
Just like black holes once were. They were pure theory for decades before we started finding real evidence.
It makes you wonder, doesn't it? What other strange solutions or possibilities are still hiding in the math, waiting for us to figure them out, or for some future discovery to completely change how we see space travel?
Exactly. The universe might still have some incredible surprises up its sleeve.
A truly provocative thought to end.